Okay, so picking up where we left off, what's the density of A of x? So it is centered at the actual value f of x. Okay. So we're going to make two notation simplifications to make our notation easier to work with. One, we're going to set delta equal to we're going to denote the global sensitivity of f by delta, and I'm going to use mu to denote f of x, and similarly mu prime to denote f of x prime. Okay, so now what's going on is that our density h x y, as I said earlier, it's a product of a bunch of different terms. So the first term is for the first component of y, and so it's going to be based on the difference between y and the first component of y and the first component of mu times epsilon over delta. Okay, so this is sort of the contribution to the density that comes from the first component, and it's based on how far y1 is from mu1. Contribution from the second component is going to be based on how far y2 is from mu2. Okay, and again, each of these is being multiplied in the exponent by epsilon over delta, because that's the scaling factor. We're scaling the distribution by delta times epsilon. Okay, so times dot dot dot, so that we have d of these terms. The last one is like epsilon over 2 delta times e to the minus y to yd minus the dth entry of mu times epsilon over delta. Okay, so we can kind of clean this up a little bit by collecting these terms. So we've got d factors of epsilon over 2 delta. And there are d of those. And then what's going on in the exponent? So if I look at sort of, this is, here I'll write it this way because I can write bigger this way. So this is minus epsilon over delta. That's a common factor. And now I'm adding together all the exponents that I've got in my various terms. And what's going on? This is a sum of absolute values. And so it's actually the L1 norm of a vector, right? It's actually the L1 norm of the vector y minus the vector mu. Okay. So this is a nice compact form for the density. And so it allows me to then compare what happens if I look at the density at y for when the input is x versus what happens when I look at the density at y when the input is x prime. Okay, so now I'm taking the ratio of these two terms. So I'm going to, I'll just write it out. So this is 2 delta to the d times e to the minus epsilon over delta y minus mu epsilon over 2 delta to the d e to the minus epsilon over delta, and now times y minus mu prime. Okay, so the y's are the same in the numerator and denominator, but the mu's are now, one is mu corresponding to f, one of the mu's is f of x and the other is f of x prime. Okay, so now the normalizing factors cancel, and what we're left with is e to the minus epsilon over delta times the difference between how far y is from mu and how far it is from mu prime. Okay, now exactly what this expression evaluates to is going to depend on which y we're looking at. But, you know, if we imagine sort of projecting things into 2 dimensions, which, you know, they're not, but we'll just draw them that way. So here's mu prime, and here's some y over here. Okay, and we're interested in the difference between the length, the L1 norm of y minus mu, and the L1 norm of y minus mu prime. And what's sort of not very hard to convince yourself is that the L1 norm satisfies a triangle inequality, just like the L2 norm, the normal Euclidean length of vectors. And so this this difference here, this is never more than mu minus mu prime, the length of mu minus mu prime, and it's never less than minus the length of mu minus mu prime. Okay, so it just basically can't be too big. If mu and mu prime are close together, then the difference of the distances from mu to y and from mu prime to y just can't get very big. And so what we get is that this whole expression is always bounded above by e to the epsilon over delta times the length of mu minus mu prime, which by assumption is at most delta, because it's at most the global sensitivity. So this is at most e to the epsilon, since mu minus mu prime is less than or equal to the global sensitivity, which is the same thing as delta. Okay, so what have we got? What we've proven is that the ratio of the two densities, so we're comparing like two different Laplace distributions, right? One centered at mu, okay, so it's this multi-dimensional thing, but who knows? One centered at mu prime. Okay, so we're comparing these two distributions, and what we've got is their densities are not too far apart. So in order to complete the proof, let's consider some event. Some subset of R to the D, and it has to be a measurable set for its probability to make sense, but we're not going to worry about that. Let's just assume it is, and we're not going to define measurability too carefully. So now the probability that A of x lies in E, that's exactly equal to the integral over all the possible vectors y and e of the, the density of the density h sub x evaluated at y. Okay, so these, just to be clear, we're working with vectors, so these are all vectors. And what we said is that, like, term for term, this is always less than e to the epsilon times what we would get if the density were evaluated for the distribution of a of x prime. Okay, and now we can pull the e to the epsilon out front, and what we're left with is just the integral of the density for x prime, for a of x prime, over e, and that's exactly the probability that a of x prime is in e. Okay, so this last part is very standard. So once we've established that the densities are close point for point, then by just, we can just automatically conclude that they're close for all sets E. Okay, so that proves our statement that we're trying to prove. Okay, so what have we done? We've seen this Laplace mechanism, and we've seen some examples of some functions that sort of fit the framework of where we can bound their global sensitivity. The last thing I'd like to do is just give you some tools for analyzing the accuracy of the Laplace mechanism a little more generally, and because we're going to need these in class. So the first tool is just, basically when we want to analyze the Laplace mechanism, we're looking at these Laplace random variables, the Laplace noise we're adding, and we want to understand like how big it can be. So one useful thing that I mentioned earlier is that if z is drawn from the distribution Laplace lambda, like in one dimension, just one real number, then the expected absolute value of z is lambda. And then you can also prove a tail bound. So you can prove that the probability that z exceeds any multiple of lambda drops off very quickly as that multiple gets big, right? So again, the distribution looks like this. And so as you go out farther, here's lambda roughly. If you go way past lambda, if you go out to like t times lambda, then the probability mass that remains up here is at most e to the minus t. In fact, pretty much exactly e to the minus t. Okay, so sometimes when we're considering this mechanism, we're going to want to be able to think about not just like not just the execution of the Laplace mechanism with one-dimensional outputs, but with high-dimensional outputs. And so let's think about how that might look. Suppose we've got now not one Laplace random variable, but d Laplace random variables, each IID with the same distribution with parameter lambda. So we can say there are some things we can say very easily about them. Oops, sorry. So one thing we can look at is sort of like, well, what's the expected, let's say, L1 noise, L1 norm of this vector? So we can look at the expectation of the L1 norm of Z1 through ZD. So the L1 norm, remember, it's just a sum of the absolute values of these guys. So by linearity of expectation, that's going to be, so that's the expectation of a sum of absolute values. By linearity of expectation, that's the sum of the expected absolute values, which is equal to d times lambda. So that's one useful thing to be able to keep in mind. But the other thing we want to understand is, well, how big is the largest entry of the ZIs? Because, for example, if we're releasing a histogram, we want to know not just like what is the typical error for any particular bin, but how bad is the error of the worst bin? Okay. So one way to capture that is to define a random variable m, which is the maximum of a bunch of these ZIs. And a useful fact is that the expectation of m is lambda times, is at most, well, it scales with lambda, so at most lambda times the natural log of d. Okay, so the worst error doesn't increase, the magnitude of that, the expected magnitude of the worst error doesn't increase too quickly as the number of entries of the vector increases. Okay, and this is just a consequence of this property here follows from this one up here. Okay, by a union bound. Well, okay. Actually, what the union bound implies is, sorry, this one down here, and then there's an implication like that. So the other useful property is a tail bound, which just says that for every t, the probability that this maximum exceeds lambda times log d plus another t multiples of lambda is at most e to the minus t. Okay, so basically what this says is that the m, if I look at the distribution of m, it's, once you pass, and so who knows what happens up till like lambda times log d, but then once you pass that point, it starts drop off exponentially. And if I look at what happens at lambda times log d plus t, then again, what I get is that the mass under the tail is at most e to the minus t. Okay, and perhaps if we have time in class, we'll discuss how these are proved. But I will stop there.